How's it going, everyone? The other day was my birthday, so I thought I would do something kind of fun on this channel. Hopefully, you guys think it's fun as well. We're going to be reading a paper. I'm going to read this entire paper here today, word for word, and I don't know, speak about what I think about it and maybe take some notes. Yeah, let's get started. So, this is a free article I found. You could copy paste this into your browser and find the same article. Title is Graphene Oxide Modified Metallic Lithium Electrode and its Electrochemical Performances in Lithium Sulfur Full Cell Batteries and Symmetric Lithium Metal Coin Cells. We got the authors over here, and we got the abstract, which is the thing I read that got me interested in this paper, so I downloaded it. So let's take a look at the abstract. This is like a nice summary of the whole paper. The paper is 8 pages. 2 pages are references and stuff, so around 6 pages. So the growth of dendrites greatly hinders the practical applications of lithium metal batteries. In this work, we adopt an automatic spreading method to coat graphene oxide GO layers on metallic lithium foil to form a composite electrode. The GO graphene oxide layers are distributed homogeneously, and show low roughness on the metallic lithium foil. The electrochemical performance of the graphene oxide modified lithium GO/Li electrodes have been thoroughly studied. The graphene oxide lithium electrode displays enhanced electrochemical performances in a lithium sulfur full battery and better cycling stability in symmetric lithium metal coin cells than the unmodified pure lithium electrode. Interesting. In addition, the growth of the dendritic lithium is successfully suppressed in the GO/Li electrode. Damn! Alright. So, personally, why I thought this was interesting is because of this, dendrites, and also this. So, yeah, graphene oxide is pretty interesting to me, and dendrites are pretty interesting as well. And it's also cool that these guys made a lithium symmetric coin cell. Let me highlight this as well. And it's cool they made a lithium sulfur full battery. So yeah, those are kind of the things that jumped out at me, and I was like, cool, let's read this. So before I move on from this, normally how I read a paper is I read the title, I read this thing, and then I just kind of zoom through all the papers or all the sections. So we got introduction, 1, 2, 3, 4 paragraphs on the introduction. Then we have experimental, which is the second section. 2.1 material fabrication, 1 paragraph here. 2.2 characterization. We got a little picture here. 1 paragraph on characterization, 3 paragraphs, and then the results and discussion. Another picture over here. Pretty big picture, a lot of little smaller pictures inside of it. But the results and discussion has like 1, 2, 3, 4 paragraphs here. This entire slide is just images. Actually, there's a bit of text over here and here, but 2 big kind of figures. And then a bunch of stuff in the discussion conclusion section here, and some other data over here. And we got another picture, some more paragraphs, another picture, and then it ends over here with the conclusion, which is 1 paragraph, some acknowledgments, and all the references. Cool. So just looking at that to see like how long is this movie that I'm gonna sit down and watch. If I'm sitting down to watch Titanic, I want to have some good snacks. I got some tea right here, so we're gonna start off chronologically from the introduction and read through. So let me zoom in, see what we're working with here. So the introduction. Rechargeable lithium-based batteries such as lithium sulfur, lithium air, and lithium ion batteries have been extensively studied for electrochemical energy storage because of their high working voltage, large energy density, and long life cycle. And then they give 1 to 7, which are the references that they are citing for this specific paragraph. Okay, cool. I'm not going to really talk about each sentence here. We're just going to read. Maybe I'll jot down or like highlight some stuff that I think is quite interesting. It's just going to be a read through. However, all these batteries use Li metal as the anode and encounter great challenges as the formation of lithium dendrites during cycling causes great safety hazards. Citation 8. Okay, so great safety hazards is cool to highlight, you know, you don't want that. And I guess here they're kind of introducing the problem, like why are they doing this research? Constructing a stable and effective solid electrolyte interface, SEI over here. Normally whenever they have something abbreviated like this, for the rest of the paper, they're not going to call it solid electrolyte interface. They're just going to call it SEI, which can get quite confusing. If you have a paper that has a billion jillion acronyms, you can get kind of confused. So maybe I'll just refer to this as solid electrolyte interface. Might make the video longer. Anyway, so constructing a nice solid electrolyte interface is one of the most effective strategies to inhibit the dendrite growth and thus to achieve a superior cycling performance. 9 to 11. Okay, they cite this as well. It's important to keep track of what are these references they're referring to. They're at the end of the article, so you can kind of check these to see what they're talking about. Where did they get this idea from? For example, the solid electrolyte interface on the graphite anode can be extremely stable during several thousands of cycles in the carbonate electrolyte. The Li-ion batteries, lithium-ion batteries, with the graphite anode have been successfully commercialized. Okay, so carbonate electrolyte is interesting to me because they kind of just introduce it here out of nowhere. They never mentioned this before. They also mentioned graphite anode, lithium-ion batteries, graphite anode, stuff like this, but this is kind of interesting to me, like why are they using this electrolyte? And lithium-ion batteries normally don't have lithium metal in it, so I'm not too interested in looking at this deeper. Anyway, maybe I'm just randomly. We're going to continue. However, the solid electrolyte interface layer of lithium metal is usually unstable. Okay, interesting. Usually unstable. Check my phone here. And it is not yet well understood. Okay, actually this entire sentence here is pretty interesting. However, the SEI layer of lithium metal is usually unstable and is not yet well understood. So that's why I didn't really care about this lithium-ion batteries, because they say that graphite, which is the anode in lithium-ion batteries, has been successfully commercialized because the graphite is extremely stable. Right? So the SEI that forms on graphite is extremely stable. The following sentence says, the SEI layer on the lithium metal is really unstable and is not yet well understood. So they haven't commercialized it yet because of these great safety hazards from the lithium dendrites. Very cool. Compared with volume changes of graphite, 10%, and silicon anodes, 300%, respectively, the relative volumetric change of the Li metal is virtually infinite. What does that mean? Because Li metal is hostless. I'll do relative volumetric change of Li metal is virtually infinite. I'm not too sure what that means exactly. I mean, they're saying that graphite can change in volume by 10%, graphite in the battery. Silicon in the battery can change by 300%, so it can grow, it can literally triple in its size. Graphite only grows like 10%. It kind of like stretches and grows based on like the chemistry happening in the battery. But they're saying lithium metal has an infinite volumetric expansion possibility. I'm not sure if that's what it means. I'm kind of just thinking off my feet here. But they're saying because lithium metal is hostless, and they put hostless in quotes, so maybe I'll take a look at that after this paper. The huge volume change requires the SEI layer with high elastic modulus. Okay, interesting. So because the lithium has a greater likelihood of expanding, you need this SEI layer. By the way, this is the layer that forms between the lithium electrode and the electrolyte in the battery. That's all I'll say for that. So they put a little 14 here. The 14th reference is talking about this high elastic modulus SEI layer. Interesting. For an ideal SEI, solid electrolyte interface, it should possess several characteristics such as high lithium ionic conductivity, proper thickness with compact structure, and high elastic strength to mechanically suppress the burst of lithium dendrites. This is a cool sentence here. For an ideal SEI. And they give you some citations there as well. However, the SEI layer of lithium metal batteries is unstable in some extreme operation conditions, such as extreme high/low temperature and, going over to the other side here, high cycling rates. The formed SEI either grows much thicker or becomes non-protective, which induces rapid performance degradation. Up to now, the SEI modification methods of lithium metal are classified as follows. 1. Changing electrolyte component to stabilize SEI, such as adding additives into the electrolyte. 2. Treating the lithium metal with chosen chemicals to coat an ex situ formed protective layer. Or artificial, so I guess ex situ is artificial, on the lithium metal. 3. Redesigning the lithium anode structure to postpone the growth of lithium dendrites. Period. It is very difficult to achieve sufficient passivation between the lithium metal anodes and the electrolyte through the first method, as indicated by Auerbach, citation 40. While concerning to redesign the lithium anode structure, the third method, it is not convenient in practical application. The second approach is to make a pre-formed protective film layer with high lithium ion conductivity, such as carbon films and lithium nitrogenous compounds. The protective layer can not only prevent lithium metal anodes from direct contacting with the electrolyte, but also improve the uniformity of the solid electrolyte interface film and suppress the growth of dendritic lithium. Damn. Okay, this is quite interesting. They have 3 different kind of recommendations of how to fix the problems that we saw in this section here. And they're like, the first and the third are not good because of this person's research and because of not convenient in practical application. And then they say the second approach is pretty interesting, and that's what we're trying here today. So let's finish off with this last here paragraph on the first page, and then kind of just take a big overview of what we saw. As a two-dimensional crystal of sp squared conjugated carbon atoms, graphene sheet possesses high lithium ion conductivity and excellent mechanical strength, 41, which makes it a promising candidate as the protective layer of lithium metal anode. According to the previous reports, 3542, the graphene oxide sheets will orderly stack layer by layer after suction filtration and can inhibit the formation of dendritic lithium, essentially when composite with lithium. Unsatisfactory, the filtration of graphene oxide sheets is demanding and time-consuming. In order to simplify the preparation process, an automatic spreading method is used to cover graphene oxide film on lithium electrode. Theoretically, the liquid solution will spread evenly on the substrate under the liquid tension, and the graphene oxide sheets will flat and descend. After the organic solvent fully volatilized, there will, I feel like I'm speaking with a stroke here, there will be only graphene oxide film covered on the basal surface, and the thickness of the graphene oxide can be controlled through adjustment of the concentration of the solution. Cool. As the molecules of graphene oxide is chemical polar, as the this is weird, I feel like I'm tripping out here. As the molecule of graphene, anyway, is chemical polar, and okay, that's an interesting term too, therefore can be dissolved in polar solvent according to the principle of polarity, mutually soluble. Okay, the sentences here are a little confusing to me. Maybe it's because it's midnight right now, I'm a little tired. Unfortunately, most of the polar solvent is chemically active, is chemically activity to metal lithium. What? is chemically active to metal lithium, maybe, which made the choice of the solvent become a problem. Okay. Actually, did I want to highlight that? No. In order to choose the appropriate organic solvent, the ethanol, acetonitrile, ether, and DMC are tested, and the DMC is determined ultimately. In this present work, automatic spreading method, which use DMC as the solvent, is used to fabricate graphene oxide slash lithium electrode, and its electrochemical properties is investigated in detail. Enhanced cycling capacity and cycling life are obtained for the graphene oxide lithium electrode due to the rational modification of the graphene oxide on lithium. Okay, and that finishes the entire introduction section. So a little bit crazy. I didn't do too much highlighting here, although there is interesting stuff to highlight. I don't want to highlight the whole article, but let's look at this stuff on the big here. So we got a problem. The problem is this SEI, solid electrolyte interface, in lithium metal batteries is unstable. There are 3 ways to fix it, 3 proposed solutions, 1, 2, 3. A few of them are not the best, so this article tries to explore second one, treating the lithium metal with chosen chemicals to coat an pseudo-formed protective layer, or an artificial SEI layer. So they're trying to protect the lithium metal by creating a fake barrier, like not a fake, but an artificial engineered barrier between the lithium and the electrolyte in the battery, right? Because the lithium has like the tendency to make these dendrites, which we saw over here, growth of dendrites, and that's not good. So this second kind of strategy that they have, it has to be it has to have several important attributes. The second approach is to make a preformed protective film slash layer with high lithium ion conductivity, such as carbon films. Where did I read? So this last article, this last kind of paragraph, they talk about how they're actually putting the graphene oxide onto the lithium metal, but okay, here it is. For an ideal SEI, it should possess several characteristics such as high lithium ion conductivity, proper thickness with compact structure, and high elastic strength to mechanically suppress the burst of lithium dendrites. So it's cool because this second method that they use, I think, hits all of these things for the ideal SEI. I think graphene oxide is pretty conductive to lithium ions. I'm not too sure, but I think, I'm kind of just positing this. I would assume it is. The proper thickness is actually answered by this section here because they develop a film, and the thickness of the geofilm can be controlled through adjustable concentration of the solution. So with their strategy, which they introduce later, I guess, they can also get the proper thickness. So they have a lithium ion conductive material, proper thickness, compact structure, maybe, if it works, right? They said over here, theoretically, the liquid solution will spread evenly. So they're not even sure if this will happen. They're kind of just saying theoretically, but I'm sure they give some kind of like reasoning later on. And the final thing is high elastic strength to mechanically suppress the burst of lithium dendrites. So I think actually this also checks here. The geosheets will orderly stack layer by layer after suction filtration can inhibit the formation. Okay. Graphene sheet possesses high lithium ion conductivity. Okay, so they say it right here. It actually fits this thing right here, the lithium ion conductivity, and excellent mechanical strength. And they give this citation 41. So if you don't believe in them, you can read this article 41 that's in the bottom of the paper and see where they got this idea from. And this high elastic strength to mechanically suppress, I think, is what they mean here. Excellent mechanical strength. We don't know, right? It's just an idea. We'll see if it works. And then here they talk about their methods. So overall, interesting introduction. Let's see, we're done basically 1/6 of the paper. So we're going to keep going with the experimental section. Experimental section should go quicker. We got this section here and this section. It is like this whole second page. And we got a little picture here. So let's zoom in and see how it looks. Material fabrication, GO, which is graphene oxide, was prepared by a modified Hummers method, which was similar to our previous reports, 43 to 46. So, modified Hummers method, interesting. I'm gonna just highlight that, looks pretty cool. To prepare the graphene solution, 2 milligrams graphene oxide powder was dispersed with 10 milliliters high purity anhydrous DMC. They mentioned DMC before, I have no idea what it is, but I'm assuming it's some kind of liquid. We'll see. And then the mixture was vigorous stirring and treated by ultrasonication. Maybe there's some like kind of English grammatical stuff going on here. Cool. The graphene oxide was dispersed homogeneously and a transparent light brown solution can be obtained. The lithium foils were pasted on copper sheets with double-sided adhesive. The thickness of the lithium foil was 0.3 millimeters, while the thickness of the copper sheet was 0.05 millimeters. Then the GO/DMC solution was dropped on the lithium/copper composite belt. Okay. Under the action of liquid tension, the GO sheets would coat on lithium foil as the GO/DMC solution spreading. The GO/Li electrodes were fabricated by punching the graphene modified Li/Cu composite foil into 15 millimeter wafer. So this is like the final kind of electrode that they use, I think, for the battery tests. The area of the double side, actually I'm gonna highlight this. The GO electrodes fabricated. Boom. Good kind of summary of this whole section. Modify Hummers method, boom, 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 deposition. Here they go, 50 millimeter wafers. We could use this as a modified electrode. Right, because they say the graphene oxide/lithium electrodes were fabricated by punching ball. The area with the double-side adhesive must be avoided when punching the electrode wafer. The copper sheet was used as the current collector during the following electrochemical cycling. The schematic diagram is shown in Figure 1. Figure 1 is right here. The fabrication process of automatic spreading method fabricating GO/Li electrode. So here I'm assuming this orange is the copper and the little gray in the middle of the copper is the lithium. Here you get this like slightly brown solution, which they told you happens over here. Light brown solution can be obtained. So they deposit that. You get this sheet over here, and then boom, you hole punch that into a 15 millimeter diameter wafer, and this is your final electrode. Nice. And that looks like it's it for the material fabrication. Characterization. The microtopography of GO/Li electrodes was characterized by scanning electron microscope, SEM, Hitachi S4800 equipped with Genesis 40, okay, whatever, and transmission electron microscope, TEM, and they give you the model of the TEM too. The structure and composition were characterized by X-ray diffraction. The structure and X-ray diffraction, XRD. I'm just kind of highlighting all the methods they use to analyze this. And Raman spectra. Boom. And they give you the Raman model too. These are all different machines that you can use to characterize this electrode that they developed here. The bonded structures of pure Li and GO/Li electrodes after cycling were examined by an X-ray photoelectron spectroscopy using, so XPS, using on SCAL, whatever, electron spectrometer operating with a monochromated Al-KX-ray radiation source in a base pressure of, boom. Before characterization, the modified lithium foil was sealed with polyimide film in order to prevent undesirable reactions in air. This is super interesting. I'm not going to talk about it too much, but I'll highlight it because it is just cool. Lithium sulfur full cell batteries and symmetric lithium metal coin cells, this type, were assembled in a glove box filled with high purity argon. My bad, let me take a sip of tea and just breathe a little bit. Take a look at this whole paper here. I got some mint tea. I like drinking mint tea while reading some battery articles. Mint tea, go dummy. All right, back to reading. A little break of drinking some tea. Lithium sulfur Full cell batteries and symmetric lithium metal coin cells were assembled in a glove box filled with high purity argon. The lithium, by the way, this is done because the lithium reacts a lot in air, right? That's why they covered the lithium with this kind of film over here so that you can prevent undesirable reactions in air. So you have to assemble the entire coin cell, the entire battery. Since the battery has lithium in it, you have to assemble it in a glove box filled with argon so that you don't like degrade the material, and then you can pull the coin cell out of the glove box and use it. The lithium sulfur batteries were prepared for the characterization of the electrochemical performance. Nice. The symmetric lithium metal coin cells were used for research the stability of lithium electrodeposition. Okay. I guess this is interesting. Highlight that. They're just stating what they're doing. A polypropylene microporous film, Celgard 2300, was used as the separators because the battery has separator as a component. Actually, I should probably highlight this as well. The electrolyte of the lithium sulfur batteries, I'll also highlight this, was 1 mole by, okay, I'll actually read this, trifluoromethane. That actually rings pretty nice. I should have read it fully the first time. Trifluoromethane, sulfonamide, lithium salt. This thing, I'll also highlight this because everything I just read over here can be abbreviated as this, lithium TFSI, in a mixed solvent of 1 to 3 dioxylane, DOL, and 1,2 dimethoxethane, DME. Maybe I should also highlight these interesting liquids with a volume ratio of 1 to 1, including 1 weight percent lithium nitrate. Is this lithium nitrate? As an electrolyte additive. Okay, so this is just the composition of the electrolyte here for the lithium sulfur batteries. While a solution of 1 molar LiPF6 in ethylene carbonate and dimethyl carbonate, 1 to 1 in volume, was employed as the electrolyte for the symmetric lithium coin cells. So they just give you the electrolyte used for both symmetric coin cells. Also, take a look at this. You see how they say carbonate, ethylene carbonate? This is why I highlighted over here carbonate electrolyte. Right? They kind of just brought this out of nowhere, but over here they're actually using this type of electrolyte in their battery. So that's pretty cool. Maybe I'll Google search what carbonate electrolytes do. So this was employed for the electrolyte for the symmetric lithium coin cells. The sulfur cathode was modified by carbon black, CCB, and CO cobalt hydroxide. I have no idea, as previously reported here. The cobalt hydroxide at sulfur/CCB, so this entire modified sulfur cathode, was synthesized by simple hydrothermal method. In a typical experiment, 0.05 molar, I think this is cobalt, I'm not sure, nitrate, hydrogenated, and 0.025 molar C6H12N4 were dissolved in deionized water, followed by magnetic stirring for 30 minutes. Then 0.5 grams S/C composite and 0.01 grams polyvinyl pyrrolidone PVP were added and kept stirring and ultrasonicating to form a stable aqueous dispersion. To be honest with you, I have no idea what they're forming over here. Like maybe it's this modified silver cathode, but at this stage I'm just getting a little bit confused, maybe a little overwhelmed with all the stuff they're talking about. We're going to keep pushing. Afterwards, the mixture was transferred to a 100 milliliter autoclave and heated at 90 degrees Celsius for 2 hours. After cooling to room temperature, the product was sequentially washed and filtered with deionized water several times and dried in a vacuum oven at 60 degrees Celsius overnight. The average S, I'm assuming S means sulfur here, mass loading of the cathode is about 1.5 milligrams per centimeter squared. Maybe this is important. I'm going to highlight it just because I want to look at this and be like, this is the final result of all of this. What did this mean? I'm a little confused. Maybe I should actually highlight this in a different color. This is a little scary. I'm going to do this light pink over here. It's going to like really blow everything up for me, and I'll go back here because I'm just a bit confused with that whole section. Final paragraph of this second section. The galvanostatic charge-discharge tests were carried out on land battery system. Okay, this is just the type of battery system used. Galvanostatic charge-discharge tests seems important. I'm going to bring this back to my original. What color were we using? Looks like that one. Cyclic voltammogram tests also looks important. Were carried out using this electrochemical workstation in a potential range of 1.5 to 3 volts versus lithium plus at a scan rate of 1 millivolt per second. This also looks important. I'm going to highlight it. Final kind of sentence here. Electrochemical impedance spectroscopy also looks important. Measurements were performed on this system, which was mentioned over here, over a frequency range of this. This actually looks also important. And the amplitude was set to 10 millivolts. So, okay, this I think is also important. After the electrochemical test, the working electrodes were removed from the cells with the battery removal machine. And then they give you this. All right, let's zoom out. This was crazy. We've gone through 2 pages of the article. Let's just look back and see what we have left. So we have the introduction, gave us a bit of an idea of what's happening. Experimental, they talked about what they did. They're doing a lot of shit. Pretty interesting shit, but kind of confusing shit as well. So we're just going to keep that in mind. 3, results and discussion. I'm going to just zoom through again because I'm getting a bit like overwhelmed with how much content we have. All right, this is going to be the bulk of the reading. The results and discussion. Let's actually zoom through it. We're going to read a lot. We're going to look at pictures. We're going to have some fun. Let's take a look. Results and discussion. Let me finish my tea. Check out this cup. Pretty fitting cup, right? All right, no more tea. For the rest of the article, we're just going to be slamming water. We're going to be enjoying this article. In our assumption, great way to start the sentence. I love this. The graphene oxide sheets will disperse in the solvent evenly at the beginning. This is actually what they kind of alluded to right over here when they said theoretically the liquid solution should spread evenly. So I guess it makes sense how over here they're like in our assumption because they theorize this. They don't know if it's true yet. This is science for you, you know. So they will disperse evenly at the beginning and flat on the substrate as the solvent spread out on the lithium foil under the liquid tension. They mentioned this liquid tension quite a few times. After the solvent volatilized, the graphene oxide sheets will flat on the lithium foil layer by layer orderly. The schematic diagram can be seen in figure 2a. Let's actually zoom out and see figure 2a. Figure 2a. Schematic diagram of the automatic spreading method here. So I guess they have their little solution with the graphene oxide sheets. It looks like they just place some of it here. It's in a bubble. And then after some time, it gets flatter and flatter and flatter. And then the graphene oxide sheets, you know, you can see them. Whoops, where did I go? You can see them kind of all floating around here, but as it gets flatter and flatter, the graphene oxide sheets get flatter and flatter as well, so you should assume they coat the whole thing. But you're unsure, right? That they could kind of like not be flat, they could kind of just be floating around vertically and get squished and scrunched. So you don't know how uniform this is. This is, I guess, why they're saying in our assumption here. Whoops. So let's keep reading. We ended off right here. In order to choose the appropriate organic solvent, the ethanol acetonitrile ether and DMC are dropped on the surface of the lithium foils. Okay, so this is kind of a parameter they use in the experiment. They're saying in order to choose the appropriate organic solvent, I still think they're talking about this. They have this one, this one, this one, and this one, four different solvents. So I guess they have the graphene oxide sheets floating in four different solvents, and they want to see which one kind of coats the lithium foil nicely. So they try with four different solvents. I think they could be talking about something else here. Maybe I kind of just like dozed off, but I'm highlighting it because I think it's important. Figure 2B to E displays the digital photos of lithium foils contacted with different solvent. 2B to E. This is figure 2 right here. B to E, the digital photos of lithium surface contacted with ethanol, acetonitrile, ether, and DMC, respectively. So B, I'm assuming, is ethanol, C is acetonitrile, D is ether, and E is DMC. Boom, this is ethanol, acetonitrile, ether, DMC. So you can see they look a little different. I'm not sure why they look different. And right here underneath each, they actually have more images. Let's actually read what those are, F, G, H, K. This is right here, F to K. SEM images of the lithium surface contacted with ethanol, acetonitrile, ether, and DMC respectively. L, a SEM image of pure lithium foil. So this is pure lithium foil, right? They do this kind of deposition technique to get the graphene oxide sheets deposited onto the lithium. This is bare lithium, right? They use alcohol. You can see the graphene oxide sheets look like this. I don't know what this looks like to you, but it looks different than this, right? This is just classic lithium. This is lithium with that little solution with the graphene oxide sheets inside of it just dropped onto it. Looks a bit different. Looks a bit different in the digital and the SEM. SEM, by the way, is just like a really, really zoomed in image that you get by shooting your sample with electrons and measuring where those electrons go. So super crazy microscope, gets a lot of details. Actually, they show you a little scale bar here. This is 50 micrometers. This little distance here that you see, the little bottom side of my box, is 50 micrometers. Micro is times 10 to the 6, negative 6, times 10 to the negative 6. So 0.006 spaces there with a 5.0. That's how many meters this is right here. Very small. You can see they have different kind of views. So this one looks a bit cracked. It looks very similar to the lithium. And this one here looks pretty much identical to the lithium. Maybe it changed a little bit. I don't know. This one looks kind of bad. Like it looks very bubbly. This one looks a bit like scratchy. This one looks a bit cracked. This one, if the graphene oxide actually coated it very nicely, then I think this one might be the best DMC. But I don't know. I'm kind of just looking at this image like I have no idea, guys. So, okay, let's keep reading. B to E displays the digital photos of lithium foils contacted with different solvents, four different solvents. The reaction between the surface of the lithium foils and the ethanol, acetonitrile, and ether can be observed clearly. While there is no visible change of the... Let me zoom out a bit here. While there is no clear visible change of the lithium surface contacted with DMC. Okay, interesting. That is actually true. You put DMC on it, this looks exactly like the classic lithium. Here, you could see a dark spot in the middle. This is the ether. Here, you could see clearly some corrosion or some chemical reaction happened. Acetonitrile. Here, you could see the alcohol messed up the lithium, looks kind of icky. So all of these kind of affected the lithium. This one looks unaffected completely. Then the SEM analysis is applied to observe the microtopography of lithium surface contacted with different solvents as shown in figures F through K. We already saw those. The surface of lithium foils contacted with ethanol, acetonitrile are full of bubbles at the microscale. That's exactly what I said, little bubbles, tiny bubbles. This one actually looks like bigger bubbles than this one. Where were we at? I'm getting kind of hyped here. Are full of bubbles at the microscale. Results from the active group in the solvent molecules. Results from the active group in the solvent molecule. Okay, actually, very interesting. I'm gonna actually highlight this whole sentence here. This looks cool. The -OH, I think this is the hydroxide group. I'm not sure. Gotta brush up on the chemistry here. The hydroxide group in alcohol molecule and the C triple bond N group in the acetonitrile molecule will react with lithium, and liberation of gas will lead to the continuous stomatal morphology. Interesting. So they actually give an explanation of why these two things happen here. Because the solvents they use have like groups that mess up with the lithium. The surface of lithium foils the surface of lithium foils contacted with ether turns black on a large scale and displays a rimous morphology. What does this mean? Is there a way I can define this? Define. What is happening here? In our assumption, brother. Okay, AI assistant is not helping here. I'm just gonna go through. I don't really want to learn what that is right now. So it says the surface of lithium foils contacted with ether turns black on a large scale and displays a rimous morphology at the microscale. Maybe rimous means like cracks and stuff. Not sure. You know what? It's actually gonna drive me mad. It's just a weird word. Rimothy. Rimous is an archaic adjective meaning having numerous clefts, cracks, or fissures. Brother man. Okay. Has a lot of cracks. Nice. Interesting word of the week. It is suggested that there will be an oxidation reaction between the ether and the lithium due to the C double bond O group in the ether molecule. So this is the ether here. So they're explaining why all these things happen with the lithium here. And I'm assuming they're going to get to the DMC here. By contrast, there is no difference between the DMC contacted lithium foil, figure 2K, and pure lithium foil, figure 2K, I. I'm assuming this is I, or L, who knows, in both large and micro scale, which means that the DMC is chemical inertness to metallic lithium. Interesting. Which means, boom. So DMC is chosen to be the solvent of GO finally. Okay, this is actually fantastic. Very cool. That was super interesting to read. I don't know if it was interesting to you guys, but they went through quite a lot of stuff. This whole picture, boom. This whole picture, these two sentences could basically like summarize it, I think. Interesting. Let's keep reading. We got another little section here, and then we're going to finish with this page. I think this is the third page of the article. The microtopography and structure analysis of the GO layer on lithium foil are displayed in figure 3. Let's stop and take a look at this new figure. Figure 3, A, B, C, D, E, F, G. A, B, SEM images of lithium/GO electrodes in different amplification. This is A and B, boom, boom. So I'm assuming this is with the DMC now, because they've chosen that to be the one that they're going to use. Then we got C to E, the TEM image, HRTEM image, and SAED patterns of the GO layers spread on lithium foil. I'm not sure what that means, but cool. Other kinds of images. F, XRD patterns of GO. Here's the XRD pattern. G, Raman spectrum of GO. Here's the Raman spectrum. The surface topography of lithium graphene oxide electrode in different amplifications is shown in figure 3A and B. We just saw that. The pure lithium electrode shows a flat surface with metallic luster. Figure 2L. A, B, C, D, E, F, G, H, A, B, C, D, E, F, G, H, bruh, I, K, L. I guess they skipped I over here. Anywho, by contrast, the surface morphology of lithium foil modified by graphene layers is similar to the vast plane, and the joint between the pieces of graphene oxide sheets present a perfect connection. It can be drawn that the graphene oxide layer spread on lithium surface uniformly and continuously. Okay. I guess they answer their hypothesis in the beginning. The TEM image, HRTEM image, and SAED pattern of the GO layers spread on lithium foil can be seen in figure 3C to E. The GO sheets flat layer by layer with a slight fold, figure 3C, slight fold. Oh, maybe there's little folds and stuff over here. Not sure. Not sure about that. Flat fold figure 3C and the typical fingerprint crystal morphology of Geo can be observed clearly in the HRTEM image 3D. Okay, not too sure how to look at those or what they mean. The XRD pattern and Raman spectrum of Geo layers are shown in figure 3F and G, presenting a typical curve shape of Geo material without any other peak, which means that the DMC solvent has been volatilized completely and there is no adverse reaction happening between lithium and the solvent. This is very interesting. I'm going to highlight this whole sentence and we're just going to zoom through. Figure 4 shows the electrochemical performances of pure lithium and GO/Li electrodes in lithium sulfur batteries. This is figure 4, so we're on to a new figure, this figure. A, B, C, D, we got some graphs. Electrochemical performances of pure lithium and GO lithium electrodes in lithium sulfur full battery. A, CV curves at the second cycle. B, galvanostatic charge discharge profiles at the first cycle. C, galvanostatic charge discharge profiles and coulombic efficiency for 200 cycles. D, Nyquist plots after 10 cycles. Interesting set of graphs. Let's go back and read what they're talking about. Figure 4 shows the electrochemical performances of the lithium and graphene oxide lithium electrodes in lithium sulfur batteries. The CV curves of pure lithium sulfur and graphene oxide lithium sulfur full batteries are shown in figure 4A. So they're comparing just lithium sulfur batteries and this modified graphene oxide lithium sulfur battery. Both batteries show two main reduction peaks at 2.3 volts and 2 volts, corresponding to the generation of long chain soluble lithium polysulfide Li2SN, where N is between 4 and 8, and short chain insoluble lithium polysulfide Li2S2 or Li2S, respectively. So they're talking about these peaks over here. This peak here, boom, peak here, and then a peak here. These peaks correspond to these polysulfides, things happening in the electrolyte. And there is only one peak located at 2.4. I'm assuming right here somewhere. In the oxidation process. So I'm assuming the oxidation process is the peak here. And then they said both batteries show two main reduction peaks at 2.3 and 2. So 2.3 is around right here. You see how there's 2.4 right here. 2.3 is right below that. This is a reduction peak. And around 2 is over here, reduction peak. So two reduction peaks, right? There's the red, just classic lithium sulfur, and the graphene oxide lithium sulfur. Both have reduction peaks, and they both have one oxidation peak at the 2.4 volt, which can be ascribed to the conversion of lithium 2, sulfur 2, and Li2S into the polysulfide, matching well with the redox process of lithium sulfur battery. Okay, matching well with the lithium sulfur battery. I'm just going to highlight that because that's interesting. And they're talking about this graph here, the CV curve. The CV profiles of lithium sulfur batteries show higher current density and reaction area than the graphene oxide / lithium sulfur full battery, which can be ascribed to the poor conductive property of the geo layers. Okay. But they said graphene had good ionic conductivity, and here their data is showing that it doesn't have good conductivity. Maybe it has good ionic conductivity, but poor electrical conductivity. I don't know if there's a difference. I'm just kind of positing. Anyway, we're done with this whole section here. We looked at these graphs, we looked at these graphs. We didn't look at all these graphs, but I'm sure they're going to talk about them here. And we got this section here with a lot of reading, more reading, and then we're going to be done here. So let's just read a little bit more. The impedances of lithium sulfur and graphene oxide lithium sulfur batteries before and after the first cycle are presented in figure S1, CESI. So I think S1 is the supplementary, like extra graphs that they don't show here. I think actually If you go down, um, the work is supported. Okay. Somewhere in here they should tell you where you can get the supplementary information. So they say CESI, and then they put this little symbol here. Is this symbol shown anywhere here? ESI. What does ESI mean? Let me just take a break here, guys. Let me take a look at this. Aha! Here we go. First page of the article, right underneath the introduction, they have some extra info here, like some information about the authors. And then here they say, here's the symbol, electronic supplementary information, ESI, available. See DOI, and then they give you this DOI. You can copy paste this DOI into any browser. You should get the supplementary information. I'm not going to do that. I'm just going to read the article. But for your information, if you want to take a look at that, and for my information, since I'm going to be listening to this video later, check the ESI electronic supplementary information, which is here. It is obvious the charge transfer resistance of graphene oxide lithium sulfur battery before the first cycle is much larger than that after the first cycle, indicating the poor conductivity of graphene oxide layers. So when they say it is obvious like this, I'm just thinking, what are they talking about? I kind of want to see if I agree with them. It is obvious that the charge transfer resistance of the graphene oxide battery before the first cycle is much larger than that after the first cycle. Charge transfer resistance. Let me see here. Capacity, potential, charge transfer resistance, current density. So the only thing they have here that's talking about cycles, so take a look at this. Charge transfer resistance, I can't find that anywhere, before the first cycle is much larger than that after the first cycle. So the only thing talking about cycles here that I've seen is this plot here. They talk about cycles, cycle number. So the first cycle is all the way over here, boom, and you can see the graphene oxide lithium sulfur battery is in red over here. And they have these arrows here. I'm not sure what this means. Maybe this means charge and discharge. But anyway, take a look at this. Right here, the first dot is up here, specific capacity that's high. And then after the first cycle, it goes boom, 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 and it falls. And maybe here, somewhere around the 10th or the 5th cycle, it's fallen considerably, like from 1100 to maybe like 900 here. Boom, little drop. Maybe that's what they mean. I'm not too sure because they talk about charge transfer resistance. I haven't seen that before, so I'm just kind of guessing. But they say it is obvious, so maybe I'll highlight this as well. Is it obvious? Maybe not to me. Maybe I'm a ding dong, but we're gonna keep reading. Nevertheless, the charge transfer resistance of GO graphene oxide lithium sulfur battery after the first cycle reduced significantly, even smaller than that of the lithium sulfur battery. Even lithium sulfur battery. I'm actually not sure what they're talking about. Oh, maybe they're talking about this here? Right here, something. Geo here is like less. I don't know. I haven't looked at this plot either. This is a Nyquist plot. I'm not too sure how to read those. So, yeah. Maybe I should. Nevertheless, the charge transfer resistance of graphene oxide lithium sulfur battery after the first cycle reduced significantly, even smaller than that of the lithium sulfur battery, suggesting that poor conductivity of the graphene oxide layer won't lead to poor electrochemical performance of the graphene oxide. Okay, interesting. I'm actually going to highlight this. I'm going to highlight this in a different color, this little pink color that I'd chosen before, because I don't know what's happening here, but I feel like it's important. So I'm going to go back to that. Figure 4b displays the charge-discharge profiles of pure lithium sulfur and graphene oxide lithium sulfur batteries at 0.1 C, and then they give you this milliamp per gram sulfur after the first cycle. So this is also important. I'm gonna actually highlight this. I'm gonna highlight in my original orange. Is it this orange? No. Looks like that orange. The initial charge discharge capacity of pure lithium sulfur battery is 860 milliamp hours per gram and 840 milliamp hours per gram, while that of graphene oxide lithium sulfur battery is 1043 milliamp hours per gram and 1025 milliamp hours per gram, respectively. The initial charge discharge capacity, is that shown over here? Capacity here. Okay, let's take a look at this. Let's just look at the black lithium sulfur. So this is going over here. I'm assuming this arrow going this way means discharge. I'm not sure, but we could see that it is around 8 to 900, 8 to 900. And there's another black line over here with the arrow going this way. That one is around 1200. So there's one going left, 8 to 900, one going right, around 1200. So let's see, that was for the lithium sulfur is 8. Okay, the initial charge is 860. So I know that this line going this way means charge because this is 860. You see what I'm doing here? And discharge is 840. Hold up, I think I'm tripping again. Well, that of graphene oxide lithium sulfur battery is 1040 and 1025. Okay, I'm confused. I'm not sure what's going on here. Maybe I should do it in pink again. We'll see. Actually, we should do it in pink. The first charge discharge efficiency of graphene oxide lithium is about 98.3%, is a little bit higher than that of the initial efficiency, 97.7%. The pure lithium sulfur battery, compared with the previous results, the capacity and stability of the lithium sulfur battery has been improved, obviously. They give the previous results here. Okay, I'm getting a little bit weary here. I don't know, I'm just getting a little confused. Maybe I've been reading for a while. It's good to take breaks, but I'm going to try doing this in one shot here. For the further research, the galvanostatic charge discharge and coulombic efficiency are tested, shown in figure 4C. Bruh. So maybe they're talking about this. I don't know. Charge. Oh, they probably were talking about it. Look. 8. So right here is a discharge. Boom. Discharge because the potential decreases. So for the lithium sulfur, the discharge potential was at 8 something here. They said 860 or 840. 860 and 840. And this is for the charge, 860, discharge 840. So the charge was boom here, 860, a little bit ahead of this discharge black curve, which is at 840. And those numbers that I'm telling you is the capacity. And then you can see that the graphene oxide one is actually higher in capacity over here. So it's doing better, obviously, right? That's what they mean by this. I think they said obviously somewhere here. Anywho, that kind of makes a little bit of sense. The first charge discharge efficiency, blank, the capacity, have I read this before? Compared with the previous results, the capacity and stability of the lithium sulfur battery has been improved, obviously. Okay, I think that's what I meant. For the further research, galvanostatic charge discharge and coulombic efficiency are tested, shown in figure 4C. The capacity of pure lithium sulfur decreases from 840 to 487 milliamp hours per gram. 840 to 47. So I think 840 is here, and then boom, it drops to here, which is 487, somewhere over here. So this is this one here. Oh, and they also do coulombic efficiency in percentage on this side here. You can see this is 100%, this drops down to 40% here. After 200 cycles. Apparently, the graphene oxide lithium sulfur full battery has better electrochemical performance. Let me put this back in my original orange. So this, I think they're saying it is because they see this red as being higher than this black. So their modified graphene oxide lithium sulfur battery performs better in the coulombic efficiency and better in the capacity after 200 cycles compared to the lithium sulfur one. And then they have this other scatter plot here. I'm not too sure. Oh, this arrow means, bro, I'm such a ding dong. This arrow is telling you these plots here are for the coulombic efficiency And this arrow here is telling you that these two plots are for the capacity. So the Coulombic efficiency looks the same for the black and the red points, but the capacity is different. It looks like the black points are lower in capacity, lithium sulfur, than the red graphene oxide lithium sulfur. Okay, I think things are starting to make a bit of sense here. The Nyquist plot, which is the last plot that we haven't looked at, of pure lithium sulfur and graphene oxide lithium sulfur full batteries after 10 cycles can be seen in figure 4D. All of the plots are mainly composed of a small intercept at high frequency, an arc at high to medium frequency, and a linear part in low frequency. Okay, I think they're talking about this frequency here, maybe? I don't know. Ohms. I'm not sure how to read those yet. I'll take a look at Nyquist plots a little bit later for fun. A little bit of a bedtime story. What is a Nyquist plot? Okay, so the arc high frequency, the arc in high frequency region represents the charge transfer resistance and the electrical double layer capacitance. Cool. Highlight this. The straight line in the low frequency region reflects the conductivity at lithium plus compared to the curve shape of the pure lithium S and the graphene oxide lithium S sulfur batteries. It is demonstrated that the graphene oxide lithium sulfur battery presents a smaller charge transfer resistance and a larger lithium ion conductivity, which can be, okay, I'm just going to highlight this as well, this is important. All of this can be attributed to the protection of the geo layers. Interesting. In details, some side reactions occur on the surface of lithium anode during the initial cycling process, and the reaction products accumulated on the surface of the anode will hinder the transfer of the electrons and lithium ions. As the graphene oxide layers on the lithium surface can reduce the side reactions, there will be less side reaction products accumulated on the surface of the geolithium anode, which lead to the small charge transfer resistance and high lithium ion conductivity. Cool. This also is an interesting sentence. Come on. I'm going to highlight this one in orange. Keep reading here. Voltage versus time profiles for pure lithium and graphene oxide lithium electrodes in symmetric lithium cells are shown in figure 5. So we have voltage and we have time over here. Voltage, time, voltage, time, voltage, time. A, B, C, D. Figure 5. Voltage versus time plots in symmetric lithium cell, with each half cycle lasting 3 hours. A pure lithium electrode at a current density of 0.4 milliamps per centimeter squared. B pure lithium electrode at 0.5 milliamps per centimeter squared. C graphene oxide lithium electrode at 0.4. D graphene oxide electrode at 0.5. So two testing parameters here. A and B are just the pure lithium electrode. They have a current density here of 4.4 milliamps and 0.5 milliamps per centimeter squared. Then they have the modified C and D graphene oxide electrode at the same 0.4 and 0.5 current density. So you can see some crazy stuff is happening here. This is just the pure lithium. This here is also just the pure lithium. And these two down here are the modified lithium. Not sure what to say from this. Maybe you could look at the voltage, but we're just going to keep reading. We're going to keep reading. We ended off right here. Each half cycle lasts for 3 hours at 0.4 milliamps, 0.5 milliamps per centimeter squared, respectively. 3-hour intervals of strip/plate is chosen to allow enough lithium to transport between the electrode. Hence, the voltage change could be fully observed. Okay, this is interesting. Boom. The voltage versus time profiles for pure lithium symmetric cell at 0.4 milliamps per centimeter squared show an erratic voltage response, figure 5a. Erratic voltage response. While the graphene oxide lithium symmetric cell at the same current density maintains stably over 600 hours. Maintains stably over time in seconds. I'm assuming this is how much they mean. So boom, crazy voltage, constant voltage. Boom, crazy voltage, constant voltage until the end, crazy voltage. Cool. I guess that's interesting to know. When the current density is increased to zero point 0.5 milliamps per centimeter squared, the voltage versus time profiles for both pure lithium and graphene oxide lithium symmetric cells vibrate more violently. By contrast, the voltage versus time profiles for the pure lithium symmetric cell up and down more irregularly. The haphazard changes in the profiles indicate the poor stability of the cell, which can be ascribed to the dendrite formation on the surface of the pure lithium electrodes. All right, I'm going to highlight that. The good stability of graphene oxide lithium symmetric cell can be attributed to the protective effect of the graphene oxide film. Actually, I should erase this and highlight all of this last paragraph, last sentence of the paragraph here. Let me take a sip of water. The digital photos of SEM images of pure lithium and graphene oxide lithium electrodes after 200-hour cycling process in the symmetric lithium cell system are shown in Figure 6. Figure 6, A, B, C, D, E, F. The digital photos of SEM images of pure lithium A, B, C, and graphene oxide lithium electrodes D, E, F after 200. So this is pure lithium. This is the lithium that's been modified as per the article said. These are some images here. You can see a bit of differences. So that's Figure 6. The physical photo of pure lithium electrodes shows the surface of pure lithium electrode is rugged and local reacted, Figure 6A. So there's some little reactions happening here. Here we haven't looked at that yet. The dendrite clusters of lithium can be observed clearly after magnified in 500 times, Figure 6B. This is magnified 600 times. And you can see, I guess, all these little mountains over here are the lithium dendrites that they're talking about. While the SEM image under 5,000 times displays obvious sharp granule morphology, Figure 6C. So this is 20 micrometer scale bar here, 5 micrometers. So this is zoomed in a lot, and you can see all of these little granular dendrites. After modified by the geo layers, the surface reaction of lithium electrode is uniform and moderate, which can be obtained from the photo of graphene oxide electrode 6D. So you see it's a little bit different with the modified graphene oxide. Figure 6E and F are the SEM images of the graphene oxide lithium electrodes under 500 times and 5,000 times, both of which present a flat mossy-like morphology. So this one, I guess, is more sharp than this one. This one is sharp granular. This one is soft, uniform, mossy, granular. Mossy-like morphology. I'll highlight that. It can be suggested that graphene oxide layers can help suppress the formation of dendritic lithium efficiently. Cool. Figure 7 shows C1s, lithium 1s, and O1s XPS spectra of pure lithium and geo lithium electrodes after 200-hour cycling process in symmetric lithium cells. Here is Figure 7, A, B, C, D, E, F. XPS spectra of pure lithium and graphene oxide lithium electrodes after 200-hour cycling in symmetric lithium cell. A, C1s. I don't know what this C is. I'm going to put it here, C, L-I-O. Since there's C1s, Li1s, O1s, I think this is lithium, this is carbon, and this is oxygen. I have no idea. This is the first time I'm seeing this. Pure lithium electrode, C, okay. Interesting kind of figure here. We're going to look at that in a second. So what they have here is Figure 7A through C, these three over here, shows C1s, Li1s, and O1s XPS spectra of pure lithium electrode after 200-hour cycling, respectively. According to the NIST X-ray photoelectron spectroscopy database, the peaks at 284.7 electron volts in C1s XPS spectra can be assigned to the graphite band, G band, SP squared bonding figure. Okay, this is crazy. I'm gonna actually just highlight this whole thing because it seems interesting. Actually, I think I'm gonna put this in a pink. All right, because yeah, that is crazy. In addition, the CO bonding, COO bonding, minus COR minus COH bonding, and the lithium 2 CO3 slash CF bonding are also found at binding energy of 288, 287.7, 286.3, and 289.7 electron volts respectively. This stuff here is crazy to me, guys. I'm gonna put it also in pink. While in the Li1s XPS spectra of the pure lithium electrode after 200-hour cycles, figure 7b, this one here, there's an unknown peak at 58.2 electron volts existed except for the peak of LiO2, LiF, Li2CO3. The peak at 58.2 electron volts of Li1s spectrum in figure 7b, and the peaks at 533.2, 534.1, and 533.0 of O1s spectrum in 7c can be attributed to the complex organic compounds generated by Li and the electrolyte during charge-discharge processes. Okay, a lot of stuff to highlight here, but I'm actually not gonna highlight it because I'm a little bit spooked from highlighting too much. I got two pink things over here. I'll just assume this whole section is confusing to me. By contrast, the constituent of the surface of the graphene oxide lithium electrode after 200-hour cycles is not that complicated. Okay, there's only sp squared C Li, Li2O, LiOH, and Li2CO3 can be observed in figure 7D to F. Okay, interesting plots. I actually don't know what these are saying. We're gonna look at them more deeply. The unknown composition of the pure Li electrode can be ascribed to the side reaction between metallic Li and the electrolyte. It is obvious that the side reaction between the lithium electrode and the electrolyte can be inhibited effectively after modified graphene oxide layers. And that is it for the third and biggest section. And actually, we're done the whole article by reading this. So I know the last couple sections here with these graphs were confusing, but let's just finish off and see what the conclusions are. In summary, the graphene oxide layers have been successfully fabricated on the surface of the lithium metal by facile automatic spreading method. According to the electrochemical analysis, the graphene oxide modified lithium electrode can improve the performance of lithium sulfur battery effectively. In symmetric lithium metal coin cells, the graphene oxide lithium electrode displays better stability than the unmodified lithium electrode, which can be ascribed to the protection of graphene oxide layers. The suppression of dendritic lithium has been realized by our graphene coating strategy. Very cool. I'm going to highlight this to end off the reading of the article, and then we have some acknowledgments. The work is supported by the National Natural Science Foundation of China and the Program for Innovative Research Team in the University Ministry of Education of China. Very cool. Thank you guys for writing this paper. It was interesting to read. And that is my video here. Here are all the references. Here is the paper overall, what we've read, what we've talked about. Cool. Thank you guys for reading with me. I hope this was fun. A little bit of a fun video for everybody. And yeah, let me know what you guys want me to do on this channel. As always, thank you for watching. Peace out.